Today we're going to review a little bit of the kinematics of rigid bodies, which I believe is necessary background for understanding the dynamics of mechanisms that are used in vehicles. Let's just, for example, say the windshield wiper mechanism is a mechanism made of linkages. Linkages are used in many parts of vehicles, like the steering, for example, the suspension system, all those. So I think we need to do well in reviewing the principles behind that. So in here you have a situation where you see a rigid body in general. You have an axis in here, x, y, and z. And the point here is, for example, if we look at this point P on the rigid body that is rotating about the z-axis, the question is, what's the velocity of that point? The velocity of that point, obviously, if this is rotating like this, is going to be perpendicular to the distance between B and P. But there's a way of mathematically producing this. In this, or representing it in vector form. So if we consider the rotation about the fixed axis, the magnitude of the velocity, as if z would be a fixed axis, the magnitude of the velocity at this point would be ds dt, which would be the arc that it describes, and you can write it as r theta dot sine of phi, phi being the angle between the axis and the position of that which is the vector r. So in here, let's go to the next slide. In here, you can see it a little more clear. What I'm trying to do is the velocity of p, okay, and establish what the value would be in vector notation. So one way of doing that is to say that the velocity of the point P, and remember this is three-dimensional space, is omega, which is a vector that is along the z-axis, cross r, which would be Vp. So omega cross r, if you look at the right-hand rule here, you put the, as if you're holding that axis, or you point one finger towards the axis, and then the other finger towards the along Vp. So one of them this way, one of them this way. You will see that the direction of the cross product is this way. And that's what this tells us, that the velocity of P is the derivative of the position vector r, which is, in this case, omega cross r. See, the position vector here is rotating about the z-axis, and there's no elongation of the vector because it is a rigid body. Yeah? So the derivative is basically composed of the rotation. So this normally would be b is equal to r dot plus omega cross r. But in this case, that term is not there because r does not change in length, but rather changes because of the rotation and produces the velocity, which is omega cross r. You could represent it also as theta dot times in the k direction. That's another way of representing the omega vector. Here is a representation of what the acceleration would look like. The acceleration is the derivative of the velocity vector, and it would be the tangential acceleration would be alpha cross r, and the other one be the normal, which is the omega cross r, which produces this omega squared times r. Okay. In this case, the velocity vector is omega cross r, but you could have this omega cross r and find the derivative of that vector. In fact, what I would suggest we do is I'm going to take a little snapshot picture of this and maybe write on it. So I need one specific tool. No, I think it's in here. Hold on, this is right here. I need this to be able to write on it. Yeah, there you go. So in here, what I can do is, let's say, I'm just gonna put it over here so that you can see what I'm trying to say. We have established that V is equal to omega cross R. The acceleration has to be the derivative dv dt, which means the derivative dt of omega cross R. You remember how to find the derivative of a vector. You know that this is d of omega cross R dt plus omega cross into this omega vector. This is how you find the derivative of a vector. So in this particular case, we are going to have the derivative of this. We need to differentiate it as a cross product, and then of course this term is already this term. So I think we need to expand this a little bit to understand how we do this derivation. Maybe it might be worth doing it once, because it is something that you will something that you can refer to, not something you do it all the time. So let's switch for a second so I can write a little. Let's look at that derivation. So we do it once and once and for all, so that we understand what terms are. This is a vector. B is omega cross R. Both of these are vectors depending on time, except that R does not elongate. So R dot is 0 because it's a rigid body. But if you have this, you have that the derivative dv dt is the derivative of this vector, plus we are missing one vector omega cross into omega cross R, like this. So let's just expand this and see where we go. This is like omega dot cross R plus omega cross R dot, like this, right? And plus, so this is the omega dot, and then plus, of course, omega cross R. You see in here R dot is 0 because of a rigid body. Points on the rigid body do not move with respect to each other. So this term goes away, and the acceleration then becomes omega dot cross R plus omega cross R. See, this is where it comes from. So you could also write this, the acceleration is alpha cross R plus omega cross R, like that. See? So if we go back to what we were doing here, you will see here this. See, acceleration is alpha cross R plus omega cross R, Just wanted you to see where that came from. And that's what we are seeing here using this derivation. Comes from the very concept of the velocity, and that the derivative of the velocity in fact is the acceleration. Okay, let's go on with this. When you deal with plane motion, where the velocities of 2 points on a rigid body are not the same, then that motion is composed of a translation with one of the points plus a rotation about that point. So translation with A plus rotation about A. So this is the velocity of B is the velocity of the other point, B sub A, plus omega cross R, which is the relative velocity of B with respect to A. And that's what we see here. So we see that the velocity of the point B is the velocity of A plus the rotation of B with respect to A, and that's represented here. See, you can represent it in a vector form too. Velocity of A plus the velocity of B with respect to A equals the velocity of B. Okay. Perhaps this gives us a bit of a bird's eye view, more practical in here. If we're looking at from the top, the velocity of P is omega k cross R in this direction, but if we do the alpha cross R on this right here to find the acceleration of that point, you have that the term alpha cross R and then the one omega cross R is this other term. So alpha cross R is obviously, alpha is out of the picture, out of the screen, and then cross R, which would be a P, and then you have that would be the tangential acceleration. But the other one, omega cross R, omega is a vector coming out of the board. Put it right here and imagine yourself crossing that vector with omega k cross R. You're going to get one vector in this direction like this. And that's exactly what you see here. Okay? So that, having said this, we also should point out that in this diagram, we can relate the pictures here of the plane motion when the two velocities are different to a translation plus a rotation about the point A. And this is the representation of this in vector form, and then we should see it also for the acceleration. But in this case, one of the things that I wanted to remind you of, review, is also the concept of the instantaneous center of rotation. At every instant of time, if you take two velocities on the rigid body, draw a perpendicular to it, you're going to find this point C, which is the instantaneous center of rotation. Okay. There's another way of finding the point C with, different velocities, or if the velocities are parallel, it becomes much easier. The point C is on the perpendicular to both of those. This is the acceleration. We already saw the acceleration. Acceleration of one point is the acceleration of the other, plus the relative acceleration between the two of them. And that's what you see here. You see that this is the acceleration of B, in this case, is the acceleration of A, so this right here, plus the acceleration of b with respect to a. So that is what you see here. This would be the normal, and this will be the tangential velocity of the b with respect to a. Okay, so continuing with our review, that's the very same thing. The acceleration of b is the acceleration of a plus the relative acceleration. Okay, let's turn our attention now to our web page in here to what we were doing originally for the SEMI 143 class notes. Let's do exercise number 1. Okay, this is an important thing. If you know the certain conditions of this mechanism, you should be able to find the velocities and accelerations of points as they move. So this is going to be one of the first examples that we will build in working model 2D to be able to verify this answer and precisely predict what this mechanism would do. So here is the situation. You have this crank mechanism that this rotates clockwise with 45 RPMs, yeah, like that. And so if you do that, then this bar is going to swing back and forth like that. Do you see that? What is tricky here is that the point A is restricted to go on the slot up and down. And I wonder if everybody can see, when you restrict the motion of A to be up and down, what happens to the motion of the point B? The point B at some point is going to be in the horizontal position like that, right? And because it is a rigid body, the instantaneous velocity of B in the position shown has to be equal to A, because it's a rigid body. The moment that BC changes from the horizontal position, then the values will be different. So let's try to solve this problem by hand first, and then we will attempt with the computer. Just a review, as I said, the velocity of a point in here of a rigid body about a fixed axis, that the velocity of the point B is got to be omega close r. That's the velocity of this point. Just the review of the very same thing. The velocity of B is the velocity of A plus the velocity of B with respect to A. So then, just to remind you, the velocity of this point is the velocity of this one, which is, no, the velocity of B is the velocity of A, yeah, plus the velocity of B with respect to A. Okay, same thing over here. Velocity, relative velocity here, omega sub BA is omega cross RBA. So if we do this, important thing here is, and this is for the acceleration, but let's get to the problem itself. It's another review. You can review this path acceleration. In this case, let's just go on and see. If you calculate the velocity of the point B in the crank BC, of course it's going to be calculated using this graph right here. So the velocity of omega sub BC is 45 RPM converted to 1.5 pi radians per second. Velocity of B is omega BC times R sub BC. So this is 15. This is like 18 inches per second. Okay. So we do the diagram for each one of the bars. This is the one for the horizontal bar. The velocity of this point is 0, but this is rotation about the fixed point. So we start right in that position. And then here you have the velocity of A, and the velocity B is, because it's restricted, is constrained. At the instant, consider the position from here to here does not change. So the angular velocity in this case, if the velocity of A is equal to the velocity of B, which it is because of a rigid body, then omega is 0. That is, if the two velocities are parallel like here, then this is 0. Let's see what happened over here. There we go. How do we solve this? We calculate the acceleration also at that point, which would be omega square close r towards the point, towards towards C. That's this. Okay, so now if we determine the acceleration of the body under plane motion, here this is graph contains basically two graphs. Okay, one for the acceleration of A, one for the acceleration of D. Okay. Okay. If we look at the acceleration of A, this is what we'll come up with to find the acceleration of, using the same principle as stated before. The acceleration of A is the acceleration of another point plus omega cross r. So we calculate the acceleration of the point A. So with that, we go to this block diagram. The acceleration of D is the acceleration of B plus the acceleration of D with respect to B. And if we do this equation in here, we're gonna follow this in vector form, and then we end up with okay. This is the so we'll end up with the acceleration of D here. So this is the first thing that I would like to see that we built in working model 2D. So this is the solution, and we need to work out so that we'll do it in working model 2D. So going back in here, the first thing that we need to do is to produce the geometry of this just like it is in here, and then produce the simulation of the mechanisms using working model 2D. So we'll do that next.